Okay, guys, so it's time to go on to the next part of our lesson, section 14.3 in your book. And we're talking about Bronsted-Lowry, acids and bases still. And we're going to talk about how strong or weak those might be. So the strength of an acid is not really its concentration. That's how much is in there. A strength is how much of it, when in water, breaks into a hydrogen ion and the anion. And so if we have a strong acid, that equilibrium will lie far to products and it will ionize or dissociate nearly 100%. Weak acids are much, much less than that. Something like acetic acid, which is a weak organic acid, is actually only about 5% dissociated in water, where if we add hydrochloric acid to water, it goes into solution almost 100, well, essentially 100%. So here we have two acids, hydrochloric acid and acetic acid, and they are both 0.1 molar. They have the same concentration or the same amount of acid in each solution, but we see that the pH paper for HCl is much redder. pH is down close to 1. And for acetic acid, it's much higher. It's probably about 3. It's hard to see that it's not really as red, but trust me, it is not as red. So if it is a strong acid, we will not have an acid dissociation constant. It will just say very large if it lists it at all. If it is a weak acid, however, we will have values listed this because we have some of the reactants as well as some of the products, and we can write any kind of equilibrium constant for this like we would for any other dissociation. And so the Ka would be the concentration of H3O times the concentration of A- divided by the concentration of HA. And you'll recall I don't put water in, and that is because it is a pure liquid. So here doesn't matter what those species are, but we know that if the Ka is larger, then the acid would be stronger. And if the Ka is smaller, then the acid is weaker. And if it's no Ka, it's a strong acid. And you have to memorize what those are. And I gave you those last time. So here are a few. You'll see HSO4 hydrogen sulfate, but you don't see sulfuric acid because that Ka would be very strong. These Ka values came out of your book. It's table 14.2. So don't try and write these down. Just refer to your book if you need to find these. And you'll see that HBRO is the weakest of these, whereas HSO4 minus would be the strongest because it has the largest Ka. And you have to recall that when we have Kas, those exponents are times 10 to a negative number, so the smaller one is bigger than the larger one. Bases are the same way. They do a different reaction, however. They either donate a hydroxide directly or they take a hydrogen from water and create HBr plus and OH minus. Strong bases would again give us 100% of the hydroxide ions in solution, whereas weak bases give us much less than that. So here we have ammonia. The paper started out with that blue color, greenish color, and when we dip them into 0.1 molar solutions of ammonia and sodium hydroxide, we see that the sodium hydroxide on the right hand is almost orange. It's at almost 14. It's probably about 12. Whereas when we look at ammonia, it's probably closer to 9 or probably 8 or 9. So relative strengths of weak bases can be determined by measuring their Kb, We're very creative as scientists. We put a B when we're talking about bases and an A when we're talking about acids, and we put a W when we're talking about water. And so we would write the KB the same way we would write the Ka, which we write every other K, and it would be the concentration of Hb plus times the concentration of OH minus divided by the original concentration of the base. And so, again, the larger the Kb of the base, the stronger the base. The smaller Kb, the weaker the base. No Kb means it is a strong base and completely dissociates in water. Here are some reactions that these bases do. And we see that diethylamine or dimethylamine, the first one, has a Ka or Kb that goes to times 10 to the negative fourth, and we get down to the bottom one, and it's to the negative 10th. So the bottom one would be the weakest base. And again, you don't need to write these down. You just need to be able to look them up. So Ka and Kb are inversely related because in water they have to multiply together to give us Kw for water. And so pretty straightforward. If Kb is larger, then the Ka for that base would be smaller and the conjugate acid would be very weak. If the Ka is large for an acid, then the Kb must be much smaller, and so therefore its conjugate base is also very weak. So to the extent which an acid dissociates or donates a proton in water gives us how much of the conjugate base concentration we'll have. And if A minus is a stronger base than any proton donated by the water molecule it has captured, it would go back to HA. Therefore, HA is a weak acid because there is an equilibrium for this. If A minus is a weak acid or weak base, then it's unlikely to form for A minus to recapture that proton and from hydronium and return to HA. So something like sodium hydroxide, the A minus, I'm sorry, not sodium hydroxide, something like hydrochloric acid, when it donates its hydrogen ion into solution, it would create Cl minus. Cl minus is such a weak base that it will not reassociate with a hydrogen ion to reform HCl, because if that were to happen, it would immediately fall apart and would go back to the two products listed. So that's how you would know it is a strong acid. So here's just a graphic that shows you some strong acids and weak acids, some weak bases and stronger bases. And these are all in water because we have hydronium, water, and hydroxide as our endpoints of both graphs. And so most of our weak acids, all of our weak acids fits in between those values. So you'll notice here we have some very strong ions that completely dissociate, and there we see the hydronium ion after nitric acid. Then we have a number of acids, then we have water, then we have another number of acids that can dissociate again, and these do not undergo acid ionization in water. However, then we can make them into, and we're going to continue on, and we get to these very strong conjugate bases, or very weak conjugate bases of our strong acids, and they do not pick up a hydrogen ion in solution and return to their acidic state. And then after that we have water, and then we have things that are bases and they are strong enough to remove a hydrogen ion from water. And then we have hydroxide ions, which then would separate our weak bases from our strong bases. And we have some of the strong bases listed. So, conjugates of weak acids and weak bases are weak acids and bases, respectively. So a weak acid, its conjugate base is very weak. So pretty straightforward because they always have to multiply back to give us Kw. So to determine Ka or Kb, there are several ways to do this. You can be given that value, and then you could use it like we did in chapter 13. If you're given a pH, you can then calculate it just like you would any other K. Depending on what you're given, then it would be either Ka or Kb. So if you're given the pH, you'd be calculating the Ka. If you're given some other information with initial concentrations, then you could calculate Ka or Kb. These calculations are going to be a little harder, so unfortunately we will have to go more slowly. Please watch and see what I ask you to submit each day because it will not necessarily be the next worksheet. So, percent ionization, I'm going to cover this. And then when we start into actual calculations, I'm going to go more slowly than we would if we were together. So percent ionization is just like any other percent. The hydrogen ion concentration for an acid divided by the original concentration of the acid times 100 would give us our percent ionization. I will be posting one video at least on each type of calculation soon, probably by Monday. So I'm going to stop here because I think that's enough to carry you through to the end. And I look forward to being back together with you.